Good afternoon, this is Professor Elliott, and today we will look at the superposition method. Okay, well, now to explain to you the general procedure. So the superposition is used to solve circuits that have more than one power source, battery, AC source, etc. So you really learned to this point everything you need to know to use the superposition theorem. Essentially, you just solve the circuit using each source or battery in turn. So if you had three sources, you would essentially solve the circuit 3 times and then just combine the results at the end. So it's really nothing new. It's just a little different application, I guess. And the idea is that each load, which in our case would simply be resistors to illustrate the concept, the current through those resistors is shared by the 3 sources. So once you isolate each source, you can determine the current due to each source in turn, and then you simply add them up at the end. So it's really quite straightforward. But anyway, here we go. Okay, so the idea is we're going to solve for the currents from each source acting alone. So again, if there's 2 sources, then we'll solve it twice. If there's 3 sources, we'll solve it 3 times. Okay, so it's from each source acting alone. Replace each source with a short circuit. So if we're having 2 sources, then the one you're currently not working with, then just remove it and replace it with a jumper wire. So you just have just the one source in play. And then once you have all the resistor currents through each source individually, then we just determine the final net currents. And then once we have that, we can easily find the voltages. So it's quite easy that way. All right, let's go on. Okay, so just a very simple circuit for to illustrate the general idea. In this side, we're not going to do any math. I provided plenty of problems for you in the professor notes and homework activities. This is really just the method, how to approach these. So here we have 2 sources, E1 and E2. Okay, just note the polarities of the source. And we have 4 resistors. Don't worry about the values right now, it's not important. So we're going to solve the circuit using source E2. You can start with E1. It doesn't make any difference whatsoever. Okay, so here we have, well, first of all, I've decided to use electron flow. And you could easily use conventional flow if you so prefer. The important thing is that if you start with electron flow, you finish the whole problem with electron, or if you start with conventional, you finish the whole thing with conventional. Don't flip it or intermix it because it just won't work out. So electron flow, right? The current goes from the negative to the positive. So I've shown the current arrows there in red, and I like to just mark the currents with this number with a circle. So I just arbitrarily call them 1, 2, 3. You can do this however you like, but I find at the end it just makes things a little bit tidier and easier to keep track of. So okay, so once again, so we've taken out E1, E2 is remaining, and we just indicated the current arrow directions. Okay. Now we're going to do exactly the same thing using source E1. Okay, so E2 has been removed, replaced with a jumper wire. And now we have E1, again electron flow, those are the current directions, and I've identified the currents 4, 5, and 6, and the student will readily see that resistors 3 and 4 are in series, so of course I3 and I4 are the same current. Okay. So once we have those individual currents, then we need the net resistor current. Okay. Now here we're going to determine I1, I2, and then I3, so we'll start with I1. So I1 is the difference between currents 1 and 4. Now if I go back, all the way back to here, you see here I1, okay, I've arbitrarily called that I1, and see the current is flowing from left to right through R1. If I go forward again, I1 now, which is now in this slide called current 4, is flowing from right to left. So those currents are going in opposite directions, and when the currents go in opposite directions, they partially cancel. In fact, if the currents were equal, they would exactly cancel and there'd be no current. But anyway, so the final I1 is the difference between currents 1 and 4. Okay, so I'm not sure because I don't have any values which one is the larger one, but just take the smaller current away from the larger one, and so you always get a positive absolute value. Okay, so that would be current I1. Now for current I2, if we go back a couple slides, current I2, you see it's going R2, it's going in the upwards direction. I2 is also going in the upwards direction. So in that case, we're going to add the currents because the currents are sort of aiding each other, if you like, and they're going in the same direction. So that would give us current I2. And then finally, for currents I3 and I4, which of course are the same because they're going, they're in series. So we have going up, that's currents left to right, or up, and you look at it, current 6. And over here, they're going left to right and going down through our R4. So they're going in opposite directions. So really, you're just going to subtract currents 3 and 6, which is what I've shown there. Again, when you do in a calculator, just take the absolute value. So just make this one here always the larger one, and then it'll work out just fine. So once you record all the final currents and work them out, you need to calculate the net voltages. So this would be the voltage. If you build the circuit, take your meter, but you'd measure it. This is it. Okay. So just using Ohm's law, it's just simply the resistor current times the resistance, and then away you go. And if you so desire or needed to, you can easily calculate the power dissipation through each resistor by using any of the standard formulas. Okay, so once again, if you go to the professor notes and our homework activities, you'll find solved problems there with numbers. But anyway, this video again was just to introduce you to the basic method, and hope you found it to be helpful. Okay, great. Thank you for watching, and we'll see y'all again soon. Bye-bye.